stable, orbits, inside a black hole. Allow that thought to truly settle, to resonate through the very foundations of your cosmic understanding. For generations, we've envisioned black holes as the ultimate celestial cul-de-sacs, gravitational maelstroms where everything, even the swiftest light, ceases to be. They are the terrifying final act for dying stars, a merciless boundary from which there is no conceivable return. Within these cosmic leviathans, the very fabric of space and time is violently twisted, compressed, and distorted beyond all recognition, collapsing into an infinitely dense, utterly incomprehensible point, a singularity. It's a realm where the laws of physics, as we meticulously understand them, simply unravel. A one-way passage into the profound depths of oblivion. But what if this isn't the definitive end? What if, far from being a cosmic tomb, a black hole is in fact a magnificent, vibrant cradle of creation? What if, deep within that impenetrable, silent veil of the event horizon, something entirely different, something utterly unexpected actually exists? Something that fundamentally challenges our most ingrained, long-held concepts of destruction and ultimate annihilation. Consider the groundbreaking work of brilliant physicists like Vyacheslav Dokuchaev and his dedicated colleagues. These meticulous researchers bravely ventured into the complex equations that precisely describe rotating and charged black holes. These are formally known as Kerr-Newman black holes, and their rigorous mathematical journey led them to a truly stunning, almost unbelievable conclusion. Inside these enigmatic objects past a second, even deeper, inner boundary that we refer to as the Kirchhoff horizon, an extraordinary equilibrium can theoretically be achieved. Here, the crushing, ferocious inward pull of gravity, so synonymous with the destructive power of black holes, can be precisely and perfectly balanced by the powerful, outward surge of centrifugal force, the profound implication of this intricate cosmic dance. Stable, periodic orbits can indeed form. Pause and truly reflect on that for a prolonged moment. Stable orbits within the very heart of a black hole. This is not the chaotic, inescapable plunge into the abyss we have always pictured in our minds. This is organized, predictable, and sustainable motion, bearing an astonishing resemblance to the graceful dance of planets orbiting a star in our own familiar solar system. This theory, born from the rigorous, elegant mathematics of Einstein's general theory of relativity, even allows for the theoretical existence of entire planetary systems, vast and intricate, perpetually orbiting a central singularity. These hidden worlds would be forever concealed from our external perception, locked away behind the cosmic curtain of the event horizon. Could these inner realms even possess their own source of light and energy? The mathematical models hint at yes, suggesting they could derive it not from a distant external star, but from the singularity itself. According to some intriguing interpretations, this singularity might not be a vanishingly small point at all, but rather a glowing, vibrant ring of exotic energy. Furthermore, individual photons, those tireless particles of light that bravely fall past the horizon, can become trapped in what physicists call orbits of the third kind. These photons would then eternally circulate within the black hole's interior, creating a constant, ethereal, ghostly light, illuminating this otherwise secret inner world. Such a revelation pushes the very boundaries of human imagination. It propels us toward a hypothesis so bold, so utterly daring, that it feels as though it has been plucked directly from the most ambitious pages of science fiction. Yet, it remains firmly grounded in the bedrock of hard, verifiable mathematics and rigorous physics. What if a Type 3 civilization on the Kardashev scale, those incredibly advanced societies that have mastered the ability to harness the colossal energy output of their entire galaxy, discovered a way to construct and sustain their existence within the supermassive black holes found at the very centers of galaxies? They would be ensconced in absolute security, rendered utterly invisible to the vast external universe. They would be shielded from any conceivable cosmic cataclysm, from stellar explosions to galactic collisions, from gamma-ray bursts to supervolcanoes. They might even achieve a form of immortality, dwelling in a realm where time itself flows in profoundly different, perhaps even advantageous ways, granting them a unique perspective on cosmic history. This is not some mere mental exercise or fanciful speculation designed to entertain. It is a profound mathematical possibility, intricately woven right into the very fabric of Einstein's foundational equations. And this compels us to confront the ultimate, most audacious question imaginable. If entire, thriving worlds, perhaps even inhabited by advanced intelligences, can exist inside black holes, then could our own universe, with all its boundless wonders, its myriad stars, its intricate web of life, itself be one of them? Are we, all of us, every single atom and consciousness at this very moment, living inside a gigantic black hole that silently resides within some other, larger, utterly incomprehensible universe? This question, this cosmic query, is far more than just idle curiosity. It strikes with pinpoint precision at the very heart of the deepest, most enduring mystery in all of modern cosmology. The widely accepted standard model of the Big Bang, for all its undeniable successes and explanatory power in describing so much of our observable cosmos, begins with an inherent, deeply troubling problem. It starts with a singularity, an infinitely dense, infinitely hot state from which our entire universe is supposedly to have burst forth. But here's the critical point, the theoretical stumbling block. A singularity is not a physical object in any conventional sense. It represents for physicists an admission of theoretical defeat. It is the precise point where our most cherished and powerful theories break down, where the elegant language of mathematics itself throws up its hands in exasperation and screams that something is fundamentally wrong, something remains ununderstood, something is missing from our current lexicon of cosmic understanding. Roger Penrose, widely considered one of the greatest minds to ever meticulously study gravity and spacetime, formulated what he famously called the cosmic censorship hypothesis. This profound concept in essence states that any such singularity, any point of infinite density and curvature, must always be effectively hidden, concealed behind an event horizon. Nature, in his profound view, seems to be almost ashamed of its own pathologies, its inherent glitches, its theoretical embarrassments, and therefore chooses to meticulously hide them behind the impenetrable, silent curtain of a black hole, thereby safeguarding the predictability and coherence of space-time for all external observers, preventing them from peering into the chaos that would otherwise ensue. But what if this isn't merely a clever way for nature to hide a problem, a cosmic embarrassment that threatens to shatter our physical laws? What if this isn't just a convenient theoretical workaround designed to maintain mathematical order? What if this, in fact, is the solution? The revolutionary idea that our entire universe could have been born, not from an inexplicable void, but from the inside of a black hole, offers an incredibly elegant, almost poetic way to sidestep the intractable problem of an initial singularity. Instead of trying to conceive of our universe springing into existence from literally nothing, from an impossible point of infinite density, our cosmos could be the natural, inevitable result of the gravitational collapse of matter that occurred in another pre-existing parent universe, a universe of unimaginable scale and complexity that precedes our own. Consider the beautiful symmetry inherent in Einstein's general theory of relativity. It does not, in its fundamental structure, inherently distinguish between the past and the future. If a physical process can unfold according to its equations in one direction, then theoretically it can also run in reverse. If a massive star can undergo catastrophic collapse, traverse an event horizon, and ultimately form a black hole in our future, then the inverse process, matter spectacularly erupting from an event horizon in the distant past, is also a mathematical possibility, a cosmic counterpoint, a mirror image of destruction. Such a hypothetical object is given the evocative name of a white hole. And what does an expanding universe, seemingly emerging from an event horizon, look exactly like? Precisely like a white hole. Our universe, by this compelling and elegant logic, could in its very essence be a white hole, constantly expanding outwards from a hidden origin point. This groundbreaking idea, though seemingly novel and fresh to modern ears, is not entirely new. Its echoes can be found reverberating through the intellectual landscape of the 1930s. Back then, long before the term black hole had even entered the common scientific lexicon and captured the public imagination, visionary cosmologists were already deeply pondering the ultimate fate of a universe that might expand only to eventually recontract upon itself under its own immense gravity. They speculated, with a captivating blend of scientific rigour and poetic insight, that we might reside in a phoenix universe, a cyclical cosmos that would repeatedly expand and collapse, only to be spectacularly reborn, exploding anew each time it reached a critical, immense density, a cosmic reset. This colossal cosmic explosion, this moment of rebirth, they aptly termed a bounce, a rebound from destruction. The modern formulation of this theory takes this original bounce hypothesis and applies its profound implications not to the universe as a whole, as the 1930s cosmologists envisioned, but with far greater precision to every single black hole within it. What if a collapsing star, upon reaching an almost inconceivable density, perhaps the Planck density, a mind-boggling 10 to the power of 79 times denser than the nucleus of an atom, doesn't just vanish into a singularity, winking out of existence in an instant? What if instead, at that unimaginable point of compression, it bounces? This spectacular bounce, this nascent explosion of creation, would critically happen after the event horizon has already definitively formed around the star, sealing it off from the external cosmos. From our external vantage point, from outside the black hole, we would never ever be able to directly witness this internal cosmic birth. To any observer located externally, a black hole would simply remain, stubbornly, a black hole, an inscrutable void. But on the inside, a brand new, rapidly expanding region of space-time would burst into being. A new, vibrant universe, born from the death of a star. This audacious and profoundly interconnected concept, which has been rigorously developed and most fully articulated by the brilliant physicist Smolin, is known as cosmological natural selection. It rests upon two foundational postulates, two robust pillars of cosmic possibility that underpin its entire structure. The first, as we have already discussed in fascinating detail, is that quantum effects, those mysterious and powerful forces that govern the subatomic realm, intervene at the most extreme densities, actively preventing the formation of true destructive singularities. Instead, a bounce occurs, a moment of cosmic rebound, giving birth to an entirely new universe concealed within the heart of a black hole, bypassing the singularity problem altogether. The second postulate, even more radical and far-reaching in its implications, states that with every such cosmic birth, the fundamental parameters of physics, the precise masses of elementary particles that form all matter, the exact strengths of the universe's four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, undergo slight, random, almost imperceptible changes, like subtle genetic mutations in a biological lineage. This is a truly mind-bending thought, a revelation that forces us to reconsider the very nature of existence and our place within it. It means that our universe, the one we inhabit and meticulously observe, is not some isolated, unique, one-off entity. It is but one instance, one generation, in a potentially countless multitude of universes, each meticulously born from a black hole in a previous one. And in each of these uncountable universes, the fundamental laws of physics can be subtly, yet significantly different, creating an immense diversity of cosmic realities. It is an intricate cosmic analogue to biological evolution, but on the grandest scale imaginable. Universes, in this view, reproduce through the formation of black holes, acting as cosmic wombs, and their offspring universes inherit the laws of physics, but with these slight random mutations in their fundamental parameters, allowing for adaptation and change across cosmic generations. To fully grasp the intricate workings of this evolutionary cosmology, we must visualize an abstract, multidimensional parameter space. This is not a physical place, but a conceptual landscape, an incredibly complex, vast terrain where every single point, every infinitesimally small coordinate, corresponds to a unique, possible set of physical laws and constants that could define an entire universe. The altitude or height of this theoretical landscape at any given point is directly proportional to the fitness of a universe with those particular parameters. And what precisely defines this cosmic fitness? It is the number of black holes that a universe with those specific parameters will be capable of producing. The more black holes a universe can successfully spawn, the higher its fitness, and consequently, the more offspring universes it will contribute to the grand, ongoing cosmic ensemble. It's a competition for cosmic fertility. Most of this immense parameter landscape, one might imagine, would be a vast, flat, and largely desolate plain. These represent universes that, due to their unfavourable parameters, either collapse too rapidly to form any black holes whatsoever, leaving behind only a singular, isolated Phoenix universe descendant, if any, or they expand indefinitely, becoming increasingly empty, cold, and utterly sterile, doomed to leave no descendants at all. They are cosmic dead ends. But somewhere within this immense featureless plain, there are towering, incredibly narrow peaks, true mountains of cosmic fertility. These are the rare regions of parameters where universes, much like our own, possess the precise conditions to produce a truly vast, almost unimaginable number of black holes. Our universe, according to careful estimations, is predicted to create something on the order of 10 to the 18th power black holes, an astounding, staggering number that points to its exceptional productivity. Now let us trace the evolutionary journey through this parameter space. Picture the process beginning with a single, randomly generated universe, its defining point situated somewhere on that vast, largely barren plane within the parameter space. This initial universe will likely produce just one descendant universe, its parameters subtly, randomly tweaked by the cosmic mutation process, a minor adjustment in the cosmic code. That single descendant in turn will produce another. Generation after generation, these universes embark upon a slow, patient, random walk across this intricate landscape of fundamental parameters, blindly searching for a better configuration. Sooner or later, purely by the inexorable laws of statistical probability, one of these universes will happen to land on the rising slope of one of those cosmic mountains. Its descendants, with their parameters now slightly refined and nudged in a more favourable, more productive direction, might then climb even higher up that peak, finding greater success. As soon as a universe finds itself in a region where its parameters allow it to produce more than one descendant, a powerful process of exponential growth kicks in. The universes that have, through this iterative process, learned how to efficiently create black holes begin to rapidly dominate the population, propagating their finely tuned, highly reproductive parameters throughout the multiverse. After an enormous, almost incomprehensible number of generations, the vast majority of universes in this multiverse will possess parameters that are exquisitely close to those that precisely maximize black hole production. They are the most successful, the most fertile, and this, precisely, is the profound and testable prediction of Smolin's theory of cosmological natural selection. If our universe is indeed a typical successful member of this immense evolving population, then its fundamental parameters must be astonishingly fine-tuned, not for life, not for stars, but to produce as many black holes as humanly possible. This isn't just a captivating philosophical statement, it is a powerful, empirical, and scientifically testable hypothesis. We can, and indeed must, take the observed parameters of our own universe and pose a critical question. What happens if we slightly perturb them? If the theory is correct, if we are truly at a peak of black hole productivity, then most such changes in almost any direction should demonstrably lead to a decrease in the overall number of black holes produced. Our universe, by this measure, should reside at, or remarkably close to, a maximal peak in this cosmic fitness landscape, precisely as Smolin's theory predicts, a testament to its evolutionary success. This is where the truly fascinating, painstaking detective work of cosmology begins, an intricate unravelling of cosmic causality. How, specifically, does a universe manage to forge black holes with such prolific efficiency? Primarily, it's through the cataclysmic gravitational collapse of massive stars. And what then are the fundamental prerequisites for massive stars to even come into existence? First and foremost, you need stars to form at all, and for stars to ignite to begin their long, luminous lives, you need stable atomic nuclei. As we meticulously understand, the stability of these incredibly intricate nuclei, the very building blocks of all matter, is the result of an incredibly delicate, almost impossibly precise balance between the fundamental forces of nature and the precise masses of elementary particles that compose them. A tiny, almost imperceptible change in the mass of a proton, a neutron, an electron, or even a subtle shift in the elusive neutrino, or a slight tweak in the fundamental strengths of the strong and electromagnetic interactions, and stable nuclei simply wouldn't exist. Without that delicate balance, the atomic world crumbles. No stable nuclei means no atoms means no stars, and no stars, unequivocally, means no black holes. This immediately points to at least 5 critical parameters where even the smallest deviation in either direction would dramatically, catastrophically reduce the fitness of a universe, rendering it sterile in terms of black hole production, a barren cosmic landscape. But the intricate requirements extend far beyond mere nuclear stability. You don't just need stars, you need massive stars. These colossal stellar furnaces, the progenitors of black holes, need billions of years to coalesce, form, and evolve through their complex life cycles, radiating immense amounts of energy. In our universe, this process predominantly occurs within the swirling, majestic arms of spiral galaxies, specifically within what are known as giant molecular clouds. These immense clouds of gas and dust must be profoundly cold and exceptionally dense for gravity to successfully overcome the thermal pressure and kickstart the intricate process of star formation, pulling matter together. However, once massive stars are born, they begin to furiously heat their surroundings, blasting out radiation and stellar winds that tend to disperse the very clouds from which they formed, thereby preventing new stars from forming nearby, creating a self-limiting cycle. So, how does a galaxy, this immense cosmic ecosystem, ingeniously solve this intricate self-defeating problem? The answer, surprisingly, lies in fundamental chemistry. The crucial cooling of these colossal molecular clouds, allowing them to remain cold enough for star formation, is thanks to the presence of heavier elements, primarily carbon and oxygen, which then combine to form molecules like carbon monoxide, CO, and microscopic dust grains. These complex molecules and dust particles are incredibly efficient at radiating away excess heat, like tiny cosmic air conditioners, allowing the cloud to maintain the low temperatures essential for gravitational collapse and starbirth. Without them, the clouds would simply disperse. This means that any universe lacking sufficient quantities of carbon and oxygen would produce far fewer stars, and consequently, a dramatically reduced number of black holes. And the efficient production of carbon within stars, as the brilliant astronomer Fred Hoyle famously discovered, depends upon an astounding cosmic coincidence, a precisely tuned resonance between the energy levels of carbon and beryllium nuclei. A slight, almost infinitesimal change in the underlying physical parameters of a universe, and this critical resonance would simply vanish. Carbon would not be produced in the necessary quantities. This reveals yet another exquisitely sensitive parameter that absolutely has to be just right for a universe like ours, one capable of prodigious black hole production, to flourish and thrive. But the intricate story of black hole creation continues, revealing even more layers of cosmic fine-tuning, a delicate dance of forces and elements. It's not enough to simply create carbon and other heavy elements within the core of a star. Those elements must then be effectively dispersed and returned to the vast interstellar medium so that new generations of stars, enriched with these vital ingredients, can form from them. That monumental task is the glorious, violent job of supernova explosions. These cataclysmic stellar deaths are the universe's ultimate recycling engines, scattering newly forged heavy elements, the very building blocks of planets and life, throughout the galaxy like cosmic seeds. Not only that, but the powerful shock waves emanating from supernovae actively compress nearby molecular clouds, acting as cosmic triggers, initiating a rapid process of self-propagating star formation, igniting new stellar nurseries. Without the relentless cycle of supernovae, this entire process would be irrevocably broken, stifling stellar birth and black hole formation across the cosmos. And what then governs the spectacular universe-altering violence of a supernova explosion? The weak nuclear force plays an absolutely critical, almost balletic role. Neutrinos, those elusive ghost-like particles, born in the furiously collapsing core of the dying star, must carry immense amounts of energy outward and then precisely deposit that energy into the star's outer layers, providing the necessary energetic kick to trigger the star's blast. If the weak interaction were too feeble, too weak to interact sufficiently, the neutrinos would simply zip right through the star without imparting their crucial energy, resulting in a fizzle, not a magnificent bang. If, conversely, the weak interaction were too potent, too strong, the neutrinos would become hopelessly trapped within the core, unable to escape and fuel the outward explosion. In either scenario, no supernova. Consequently, changing the strength of the weak interaction in either direction would also drastically reduce the number of black holes by effectively shutting down the efficient distribution and recycling of heavy elements throughout the galaxy, breaking a vital link in the cosmic chain. Every single one of these intricate points isn't just a captivating theoretical story, it represents a stringent empirical test of the theory's predictive strength and robustness. And so far, remarkably, the theory of cosmological natural selection is holding up with impressive resilience. We do not currently know of a single small subtle change to the fundamental parameters of our universe that would demonstrably lead to the production of more black holes than our universe already produces. This compelling observation strongly suggests that our universe is indeed situated at, or remarkably close to, a maximal peak in this cosmic fitness landscape, precisely as Smolin's theory predicts, a testament to its evolutionary success in the grand cosmic scheme. This profound theory, with its sweeping implications, fundamentally alters the very way we perceive reality itself, challenging deeply held assumptions. It resonates deeply with a millennia-old philosophical dispute that stretches all the way back to the intellectual titans of Gottfried Wilhelm Leibniz and Isaac Newton. Newton, with his absolute vision, believed in the existence of absolute space and time, a fixed, unchanging, immutable stage upon which the grand drama of the universe unfolds, independent of anything within it. The intrinsic properties of particles, in his view, were inherent to them, absolute, and did not depend on the rest of the world existing in isolation. But Leibniz, with his more revolutionary perspective, passionately argued that space and time are not absolute containers, but are instead nothing more than a dynamic system of relationships between objects. The properties of any single particle, he believed, are intricately defined, not intrinsically, but by its complex connections and interactions with the entire rest of the universe, a web of cosmic interdependence. Cosmological natural selection stands as the ultimate, most comprehensive and elegant expression of Leibniz's relational vision of reality. The inherent properties of our universe, its fundamental laws and constants, are not absolute, immutable, or arbitrarily set. Instead, they are the intricate and dynamic result of a long, evolutionary history of relationships, adaptations, and relentless selection within a vast interconnected ensemble of other universes. Our universe is complex and structured, not by random cosmic accident, but precisely because complexity and structure are the most effective pathway, the most fertile ground to maximum reproductivity within the multiverse. It is complexity that breeds more universes. This profound exploration leads us to the very edge of our current scientific knowledge, to the elusive and highly anticipated quantum theory of gravity. Because it is precisely there, at the unimaginably small Planck scale, that general relativity, Einstein's grand theory of the very large, and quantum mechanics, the fundamental theory of the very small, must finally merge, must become one coherent framework. It is at this critical juncture that this enigmatic bounce, the cosmic rebound that gives birth to new worlds, is theorized to actually happen. What then are space and time at this most fundamental level? What does the ultimate fabric of reality truly look like when we strip away all macroscopic illusion, all our ingrained preconceptions? The answer that is slowly, astonishingly, starting to emerge from one of the leading and most promising approaches to quantum gravity, a framework known as loop quantum gravity, is nothing short of revolutionary. At the most fundamental level, there is no smooth, continuous spacetime as we intuitively perceive it. Instead, reality is composed of a discrete structure, a vibrant, intricate network of interrelationships, an almost unimaginable tapestry of quantum connections. Picture an impossibly complex, shimmering tapestry, woven from billions upon billions of ephemeral, vibrating threads. These threads are not merely in space, they are the fundamental quantum excitations of the gravitational field itself. They don't exist within space, they constitute space, they build it from the ground up. This granular, networked structure is elegantly described by the powerful mathematical language of spin networks, a profound concept first proposed by the visionary Roger Penrose. Each individual line within this intricate network carries a specific quantum number, a spin, and the nodes, the points where these lines intersect and connect, meticulously describe how these lines join together, forming the very dynamic fabric of existence, defining the geometry of reality itself. And this groundbreaking theory makes concrete, and in principle testable, predictions about the fundamental nature of reality. For example, the area of any given surface cannot simply be any arbitrary value. It is quantized. It can only assume specific discrete values, which are precisely determined by how many lines of the spin network pierce that surface and what their associated spins are. The same profound principle applies to volume. It too is ultimately composed of tiny indivisible quanta, intricately associated with the nodes of this fundamental network. Our familiar, seemingly smooth, continuous space is, therefore, merely a macroscopic illusion, an emergent property that arises from our viewing. This incredibly dense and complex quantum network from a great distance, much like observing a smooth, unbroken piece of woven fabric, where the individual myriad threads blur together into a continuous surface. The underlying reality is far more discrete, far more fundamental, a quantum mesh. But what makes this picture truly, utterly amazing is how it resonates with another profoundly revolutionary idea in physics, the holographic principle, independently put forward by the brilliant minds of Gerard 't Hooft and Leonard Susskind. This principle states that the maximum amount of information you can possibly pack into any given region of space is not, counterintuitively, proportional to its volume, as one might instinctively expect from a three-dimensional world, but rather to the area of its bounding surface. It suggests, astonishingly, that all the information describing a three-dimensional world is actually encoded on a two-dimensional boundary, much like the intricate patterns of a hologram can project a three-dimensional image. Loop quantum gravity, in its profound elegance, provides a natural intrinsic realization of this very principle. The information pertaining to the geometry of space, its volume, is contained within the nodes of the spin network, while the information defining the area of a boundary is carried by the lines that cross it. It paints a picture of a world where fundamental relationships are primary, where they form the very bedrock of existence, and where space and geometry themselves are secondary, emergent properties, arising organically from these underlying connections. This in many ways represents the ultimate triumphant victory of Leibniz's relational worldview over Newton's more rigid, absolutist paradigm, bringing a centuries-old debate to a stunning resolution. So, the very fundamental structure of space-time, according to the groundbreaking insights of quantum gravity, might not be a fixed, empty container, but rather a dynamic, discrete network of relationships that, by its very inherent nature, actively generates, fosters, and even demands complexity. It builds itself to be intricate. Perhaps the universe isn't just able to be complex. Perhaps it has to be complex to even exist in the intricate, coherent way we observe it. Could the very underlying logic of quantum cosmology necessitate that the world be structured enough, be complex enough, for the emergence of time, for the existence of conscious observers like us, and for the intricate causal dance of cause and effect to unfold within its fabric, could our own existence be a requirement for the universe to be itself? This transforms the once weird, almost absurd proposition that we are living inside a black hole into a profoundly serious and potentially verifiable cosmological statement. And every time we cast our gaze toward a black hole, whether it's the supermassive behemoth at the centre of our own Milky Way galaxy, or a distant swirling vortex in another galaxy, we might not merely be looking at a cosmic void, at a destructive force, but at a hidden gateway to another universe, at the nascent potent seed of a new world that will one day be gloriously born from our own. We could be witnessing the nurseries of creation, and this grand interconnected cycle, perhaps, possesses no true beginning and no ultimate end. It simply is, a perpetual cosmic dance of creation and recreation, an eternal engine of universal birth. But if this awe-inspiring narrative holds true, if it is not merely a theoretical construct but the fundamental truth of our existence, then every single, meticulous detail of our world, every law of nature we painstakingly uncover, every elementary particle we are made of, carries within it the indelible imprint, the cosmic echo of this infinite ongoing process of birth and rebirth. The very fabric of our reality ceases to be some absolute immutable given. Instead, it transforms into a living, breathing historical document, a profound and intricate chronicle of all the countless previous worlds that contributed to our existence. This then transcends the boundaries of mere physics. This becomes a kind of grand cosmic genealogy, tracing our lineage through an unfathomable chain of universes, a story written in the very stars, etched into the very constants of nature. Yet, for this majestic, cyclical process to even be remotely possible, the fundamental birth mechanism itself has to adhere to a very specific, precise form. And here, theoretical physics presents us with two completely different, radically divergent paths. Two distinct doors leading into the very heart of gravitational collapse, behind which lie totally separate, utterly different cosmic destinies. We're not simply talking about two slightly different flavors of the same core idea. We're grappling with two physically distinct, mathematically valid solutions to Einstein's equations that, to us on the outside, to any external observer, would appear absolutely, tantalizingly identical. This is the profound difference between a Schwarzschild black hole, the classic, non-rotating, uncharged, textbook monster of spacetime, and an Einstein-Rosen black hole, an object far better known by its more evocative names, a wormhole or a cosmic bridge. From our vantage point outside, observing these two theoretical objects, you simply cannot tell them apart. They possess the exact same mass, the same unforgiving event horizon, the same immutable point of no return beyond which escape is impossible. They are cosmic twins in appearance. But venture inside, and on the inside, everything fundamentally changes. The interior of a Schwarzschild black hole is not a static, serene place of quiet nothingness. It is a dynamic, utterly non-static hellscape. Everything that dares to cross its horizon is immediately, irrevocably committed to an unstoppable one-way journey straight to the central singularity. Motion inside such an object is only possible in one direction. Inward, always inward, with no deviation. Space and time dramatically, terrifyingly swap their traditional roles in such a way that moving toward the singularity becomes as inevitable, as utterly unavoidable, as moving into the future is for us in our ordinary experience. It is, by all definitions, a one-way ticket to complete and utter annihilation, a final, inescapable doom. But an Einstein-Rosen black hole, that truly is a whole other story, a cosmic narrative of vastly different possibilities, a glimmer of hope. Its geometry, when the intricate equations are meticulously solved in what are called isotropic coordinates, astonishingly reveals no central singularity. Instead, its mathematics describe a theoretical bridge, a cosmic shortcut, potentially connecting two separate, distinct exterior regions of space-time. Inside such an object, from the unique perspective of a distant observer, space itself is static. It does not relentlessly collapse in on itself, defying the usual fate of matter within a black hole. However, this beautiful, captivating idea in its most simplistic initial form harbours a fatal flaw. The Einstein-Rosen bridge is inherently profoundly unstable. It collapses so rapidly, so instantaneously, that nothing, not even a fleeting photon of light, could ever hope to make it through its passage before it snapped shut. It slams shut faster than you can even utter the word paradox, making any traversal utterly impossible. So, that would seem to be a definitive dead end, wouldn't it? A tantalizing path to new universes that quickly fades into impossibility, a cosmic dream shattered by its own instability. But then, a stroke of mathematical genius emerges from the annals of theoretical physics. There is a clever mathematical trick, a profound modification proposed by Wolfgang Rindler, known as elliptic identification. Without delving too deeply into the labyrinthine complexities of the advanced mathematics, the core gist of this idea is that you conceptually glue together two opposite future event horizons. This move, which at first glance might appear artificial or arbitrary, designed merely to achieve a desired outcome, has an absolutely amazing, unexpected consequence. It successfully stabilizes the bridge. It transforms a fleeting, impossible passage into a stable, potentially traversable structure, a durable cosmic tunnel. But this newfound stability, this incredible cosmic opportunity, comes at a steep price. For the bridge to remain open, for its throat to be propped open and resist the crushing forces of gravity, it must be supported by exotic matter, a hypothetical form of matter, often termed a light-like brain, that possesses negative energy. This is not ordinary matter that we encounter daily. This is stuff that has anti-gravity, material that actively pushes space apart, dynamically keeping the wormhole from collapsing in on itself. It is exotic, yes, and it violates all known energy conditions, pushing the very boundaries of what we currently understand about physics and the universe's constituents. And it is precisely here, at this cosmic crossroads, that we are faced with a fundamental choice, a fork in the road of cosmic destiny. Which path does nature ultimately choose when a star collapses? Does it take the Schwarzschild path, leading inexorably to a singularity and perhaps ultimate oblivion, a dead end? Or does it take the Einstein-Rosen path, which undeniably requires the existence of exotic, perhaps yet to be discovered physics, but which brilliantly opens up the breathtaking possibility of a new universe being born through a stable, inter-universal wormhole? The theory of cosmological natural selection, in its most compelling form, essentially argues that nature chooses the second, more expansive path. It posits that quantum effects, operating at the incredibly extreme densities near the Planck scale, act precisely like that very exotic matter, effectively creating the bounce and brilliantly transforming what would otherwise be a catastrophic, singular collapse into a magnificent new expansion, a universe reborn. The profound difference between these two theoretical models extends far beyond their mere geometric descriptions. It resides in the very essence of energy itself. If you perform the complex calculation for the total energy of the system contained within the horizon for an Einstein-Rosen black hole, you arrive at a perfectly sensible, physically meaningful value: m times c squared. It is that famous Einsteinian formula E equals mc squared, representing the rest energy of the system, a known and finite quantity. But for a Schwarzschild black hole, that exact same calculation catastrophically diverges, spiraling off into infinity. This, many physicists argue, is yet another powerful hint that the singularity is not a physical object, not a real endpoint, but rather a theoretical construct, a mathematical pathology that the theory itself is desperately trying to reveal to us, signalling a breakdown in our understanding, a limit to our current physics. Alright, so we now have a plausible, albeit audacious, mechanism. The gravitational collapse of matter in a preceding parent universe leads not to an annihilating singularity, but to a cosmic bounce, to the glorious birth of a new expanding universe. But this explanation, as profound as it is, immediately raises a new, even deeper, and arguably more vexing question, a puzzle that has haunted physicists for decades. What then happens to all the stuff that fell into the black hole? Where does all the information go? The intricate details about the star that collapsed, the planets it may have swallowed, every single atom, every quantum state that bravely or unwittingly crossed the event horizon. What becomes of that cosmic history? This, ladies and gentlemen, is the infamous black hole information paradox, one of the most agonizing, persistent headaches in all of theoretical physics. According to the foundational principles of quantum mechanics, information in its purest form can never be truly destroyed. Ever. It is one of its most fundamental, inviolable tenets, a cornerstone of our understanding of the universe. Yet, according to classical general relativity, everything that falls into a black hole is, by definition, lost to the universe forever, erased from existence within our spacetime beyond recovery. And to compound the problem, the black hole itself, over an unfathomably long timescale, can eventually evaporate through the emission of Hawking radiation, a faint thermal glow, leaving behind nothing but this radiation, which by its very nature is utterly devoid of all specific ordered information that defined what fell in. So, a star becomes mere heat. So where, precisely, does it go? Where does the information truly vanish? Stephen Hawking himself, for decades, famously argued that information simply vanished, was utterly destroyed, suggesting that black holes were indeed the very places where quantum mechanics finally broke down, where its ironclad rules met their match, a fundamental limit to its power. But a significant number of physicists, including the pioneering 't Hooft and Susskind, simply could not accept that conclusion. It would, they argued, violate the very foundation of how we understand the fundamental world, ripping a fundamental hole in the fabric of physical law, an unacceptable loss of cosmic memory. And this is precisely where the theory of universes residing inside black holes offers an incredibly elegant, almost poetic way out of this paradox, a resolution that beautifully intertwines destiny and cosmic recycling, a solution born from within. The information, in this profound view, isn't lost, it isn't destroyed. It is instead recycled. The entire complex structure, all the intricate quantum states of the matter that bravely or accidentally fell into the black hole, they don't simply disappear into a destructive singularity. Rather, they become the genetic code, the precise initial conditions for the new nascent daughter universe that emerges from the bounce. The subtle parameters of physics in this new universe that we talked about earlier, those are the recycled information, encoded and transformed. Our universe, with all its astounding richness, its intricate complexity, its very laws and constants, could be a direct and beautiful consequence of what fell into a black hole in a parent world. The information paradox by this compelling logic is not merely resolved, it's elegantly dissolved, because a black hole is revealed not as a cosmic tomb, but as a vital, active channel for information to seamlessly pass between generations of universes, an eternal cosmic inheritance, a continuous stream of creation. This is a breathtaking, almost overwhelming picture of cosmic interconnectedness, a grand tapestry woven across time and multiple universes. But a critical question lingers, one that demands a rigorous answer. Isn't this all just a little too good to be true? Is this merely a beautiful mathematical fairy tale, an elaborate game of the mind with no tangible, verifiable connection to our physical reality? To be considered true science, a theory must fundamentally make testable predictions. It must offer us a chance, however small, to prove it wrong, to falsify its claims, to find its limits. And how can we possibly test a hypothesis about what happens inside a black hole if, by its very definition, we are forever barred from directly looking inside, from peering beyond that impenetrable veil of the event horizon? How do we observe the unobservable? The answer, incredibly, might come from where we least expect it. Not from the inside, but from the outside, through the subtle yet powerful ripples in space-time known as gravitational waves. When two black holes spectacularly merge, when these cosmic behemoths collide and coalesce into a single larger entity, they violently shake the very fabric of space-time, creating ripples that propagate across the cosmos at the speed of light. And we, with our ingenuity and technological prowess, have learned to detect these faint, crucial ripples with highly sensitive instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory, and Virgo. The distinct gravitational wave signal from such a cosmic merger unfolds in three characteristic phases. First, the in-spiral phase, where the black holes gracefully spiral inward toward each other, radiating energy. Second, the merger itself, the cataclysmic moment of their violent union. And finally, the ring-down phase. That last part is when the newly formed, highly distorted black hole, much like a giant cosmic bell that has been struck, vibrates and oscillates, emitting gravitational waves until it finally settles into its ultimate, stable, and quiescent shape. The precise frequencies and the decay rate of these characteristic vibrations, these are known as quasinormal modes, are uniquely and unequivocally determined by the black hole's mass and its spin. They are in essence its gravitational fingerprints, as unique and identifying as a human's. And it is precisely here that the crucial key to testing this theory might lie. If black holes are not simply singularities, those simple, collapsed points of no return, but are instead cosmological black holes containing entire universes inside them, then their internal structure must be subtly different. And that difference, however small, should manifest as subtle but detectable differences in their characteristic vibrations, their distinctive quasi-normal modes, like a slightly different hum from a different kind of bell. One might logically think, there's our test, it's simple enough. Just compare the observed gravitational wave signal with the precise predictions for a regular, standard Schwarzschild or Kerr black hole against the predictions for a cosmological one. But nature, as is so often the case when we probe its deepest mysteries, is far more clever, far more nuanced, and far more deceptive than we initially assume. There exists a sophisticated mechanism that physicists refer to as mode camouflage. The critical point is this. The initial part of the ring-down signal is predominantly determined by the wiggles and distortions of spacetime that occur outside the black hole, in a specific precarious region known as the light ring, a narrow unstable orbit where photons can temporarily circle the black hole before either escaping or being drawn irrevocably in. And this external region, which dictates the initial strongest part of the signal, is essentially identical for both types of black holes, both the standard and the cosmological ones. The crucial difference is those faint telltale signs caused by the unique internal structure of a cosmological black hole only begin to show up later in the ring-down phase, after the stronger, more dominant external disturbances have largely died down and the subtle internal fluctuations finally start to dominate the signal, revealing their true nature. And this is where the harsh, pragmatic reality of our current technology comes directly into play. The LIGO and Virgo gravitational wave detectors, magnificent as they are, operate within a very specific limited frequency range. And it turns out that for the stellar mass black holes they predominantly observe, those formed from the collapse of individual massive stars, the predicted frequencies of these crucial internal modes, the very ones that could potentially reveal the cosmological nature of a black hole, are unfortunately outside their current detection range. The signal at those frequencies is simply too weak, too faint, and at too low a frequency for current instruments to pick up. This doesn't necessarily mean that LIGO isn't detecting cosmological black holes right now. It simply means that, at present, it cannot definitively tell them apart from the more conventional, regular ones. Nature, it seems, is still meticulously guarding its deepest, most profound secrets, keeping them just beyond our technological reach for now, hidden in plain sight. But this, crucially, is not the end of the story. It is merely the beginning of an exciting new chapter in our cosmic quest, a journey into the previously unobservable. In the coming decades, humanity has an incredibly ambitious plan to dramatically expand our observational capabilities into space. The plan is to launch a revolutionary space-based gravitational wave detector called LISA, the Laser Interferometer Space Antenna. This will be a truly monumental observatory, a giant triangle formed by 3 precisely positioned satellites, intricately connected by exquisitely tuned laser beams, with each side of this cosmic triangle stretching millions of kilometers across the vast emptiness of space, forming a detector of unprecedented scale. LISA will possess an unprecedented sensitivity, capable of detecting gravitational waves at much, much lower frequencies than its earthbound counterparts, LIGO and Virgo, penetrating deeper into the cosmic hum. And here's the game-changing revelation. Right within LISA's optimal detection range, which spans from 10 to the -1 to 10 to the -5 Hz, is precisely where the predicted frequencies of the internal vibrations for supermassive and intermediate mass black holes are theorized to lie. These are the frequencies that would betray their hidden nature. This means we have a real, tangible and exhilarating chance in the foreseeable future to finally put this profound theory to the ultimate test. LISA will effectively be able to hear the faint, lingering echoes emanating from inside a black hole. It will have the unprecedented capacity to pick up the very subtle vibrations that carry the unique, telltale information about what is truly hidden behind the impenetrable veil of the event horizon. Perhaps one day we will receive groundbreaking data from the spectacular merger of 2 colossal supermassive black holes, and the subsequent meticulous analysis of their ring-down phase will, against all conventional expectations, show undeniable deviations from the standard model of black holes. If this occurs, it would signify something far more profound than just the detection of gravitational waves. It would mean that we had, in that moment, detected nothing less than the birth of a new universe. Every such observation, every cosmic ripple measured, wouldn't just be an observation of a black hole, it would be an astonishing direct observation of an entire universe, teeming with its own dark energy, silently expanding and evolving, hidden from our direct view, but finally audible through the very fabric of spacetime itself, a whisper from a new creation. This incredible journey of understanding inevitably brings us face to face with perhaps the most difficult, the most mind-bending problem of all, the enigmatic, perplexing problem of time itself. If our universe, with all its immense history, was indeed born from a cosmic bounce inside a black hole, then what precisely constitutes the beginning? What, if anything, existed before the Big Bang? And how, in such a radically conceived scenario, does time itself fundamentally behave? Does it even exist in the way we perceive it? Einstein's general theory of relativity unequivocally tells us that time is not an absolute immutable entity. Its relentless flow is profoundly relative, intimately dependent on the strength of gravity and the relative speed of observation. Inside a black hole, particularly as an object approaches the event horizon, time for that falling object, from the perspective of an outside observer, appears to slow down dramatically, almost grinding to a complete, agonizing stop. Yet, for the object itself, from its own internal frame of reference, time continues to flow normally, seemingly unaffected, its own clock ticking steadily. What could this possibly mean for an entire universe, born and expanding within such an extreme time-distorting environment? Does it perceive time differently? Here, we are truly stepping into a territory where the rigorous, empirical framework of physics gracefully merges with the profound, speculative depths of pure philosophy. One of the most radical and thought-provoking views on the fundamental nature of time, particularly in the intricate context of quantum cosmology, comes from the brilliant physicist Julian Barbour. He boldly argues that time as we universally experience it, as an inexorable, continuous flow from an unchangeable past, through an ephemeral present, into an uncertain future, is, in fact, an illusion. A deeply compelling, but ultimately illusory construct of our perception, a narrative we build. According to Barbour's groundbreaking hypothesis, fundamental reality, at its most basic level, does not exist in time at all. What truly exists, he posits, is a timeless, immense, and incredibly complex space encompassing all possible configurations of the universe. He eloquently calls this conceptual realm Platonia, in a beautiful homage to Plato's eternal world of perfect ideas. Every single point within this boundless, multi-dimensional space represents a unique moment, a single, complete snapshot of the universe with all its intricate contents, all the complex relationships between its myriad parts meticulously defined. All these innumerable moments, he argues, exist simultaneously, or more accurately, outside of time, beyond the conventional temporal flow. It is in essence a gigantic static heap, or an infinitely vast deck of cards, with each individual card representing a distinct, possible now, all laid out at once. So, if fundamental reality is timeless, if all moments exist simultaneously, where then does our profound, deeply ingrained feeling of the continuous flow of time, our subjective sense of linear history, our cherished and vivid memories truly come from? Barber contends that this compelling sensation is a property not of time itself as an external dimension, but rather an intrinsic property of the moments themselves within Platonia. Certain moments within this colossal heap are intrinsically structured in such a way that they contain coherent information about other moments. He refers to these as time capsules. Our present now, the very moment we're experiencing, is one such time capsule. It contains our memories, which we instinctively interpret as verifiable records of a past that truly occurred. It contains ancient fossils buried deep within the Earth, the lingering cosmic microwave background radiation permeating the cosmos, intricate geological strata. We meticulously rid all of this as powerful, irrefutable evidence of other moments that we firmly believe existed before ours, creating a perceived sequence. Our consciousness, he suggests, acts much like a sophisticated movie projector. It is not simply randomly looking through this immense deck of cards, jumping erratically from one snapshot to another. Instead, it is following a specific coherent path, a narrative thread, where each subsequent frame logically and causally follows from the previous one, meticulously constructing the profound illusion of a continuous film, the compelling illusion of a coherent, unfolding history. Time, in this radical and beautiful view, is not a mighty river we are passively floating down, being carried along by an external current. Time is, instead, a deeply personal and subjective path our consciousness actively carves through the timeless static landscape of all possible realities, selecting a coherent sequence from the infinite possibilities. This idea, as counterintuitive and crazy as it may initially appear, possesses an elegant power. It beautifully solves the ancient philosophical and cosmological problem of the beginning of time. There is no absolute beginning in the conventional sense, because at the most fundamental level, according to Barber, there is no intrinsic time, no initial tick. The Big Bang isn't a singular point in time, a moment zero from which everything began. It is rather a special, unique moment within Platonia, a particular configuration of very low complexity from which the longest, most coherent and most intricate stories or histories can be logically constructed and experienced. It's a starting page in a book of infinite pages. And this profound concept, like all the preceding ones we've explored, once again hinges on the fundamental, undeniable necessity of complexity. To build a meaningful, coherent history out of a vast heap of moments, those moments must be sufficiently structured, richly diverse, and intricately interconnected. A random, disorganized collection of chaotic configurations, a heap of cosmic noise, will simply not generate the powerful, compelling illusion of time or any coherent narrative. The world, for time and history to emerge, has to be arranged in such an exquisitely structured way that time capsules can exist, ensuring that the present moment always contains the indelible imprints, the echoes, and the verifiable records of countless past moments. Complexity is the crucible of time, and so the grand circle of inquiry closes, bringing us back to our starting point, but with a vastly expanded, profoundly richer understanding. We see that no matter which profound angle we approach this overarching problem from, whether it's the astonishing fine-tuning of fundamental constants, the perplexing black hole information paradox, the tantalizing observability of gravitational waves from deep within cosmic mergers, or the very enigmatic nature of time itself, we consistently, almost inevitably arrive at the same overarching conclusion. The universe has to be complex. Not merely that it can be complex, but that it must be complex. Complexity is not a random incidental byproduct of existence. It is instead a necessary foundational condition for the very existence of a world where there are discoverable laws, predictable causality, the relentless flow of time, and ultimately us, conscious, questioning beings capable of observing, interpreting, and making sense of it all. Without complexity, there is no story, no observer. Perhaps the profound answer to the ancient, enduring philosophical question, why is there something rather than nothing, is simply that nothing is just too profoundly simple. And any sufficiently complex, self-consistent logical system, capable of self-organization, capable of perpetuating itself through cycles of creation, inevitably gives rise to a world uncannily like our own. A world where the intricate tapestry of space and time are born, not from an empty void, but from a timeless quantum chaos, a substrate of pure information and relationship. A world where the cataclysmic collapse of stars in one universe doesn't lead to an end, but instead sparks new big bangs, new beginnings in others. A world where the very laws of physics dynamically evolve, not arbitrarily, but specifically to maximize complexity, diversity, and the sheer potential for existence and consciousness itself. And we, with all our accumulated knowledge, all our technological marvels, all our soaring dreams and profound, fundamental fears, are but a fleeting, yet inevitable, ripple on the surface of this infinite, boundless ocean of being. We are, in a very real sense, the universe's own intricate mechanism for knowing itself, for observing its own grand unfolding, for telling its own story. And the awe-inspiring, almost overwhelming realization that our home, our entire vast star-strewn universe, might be just one of countless cosmic grains of sand hidden behind an event horizon in some other, impossibly larger, utterly incomprehensible world, that doesn't diminish our significance. On the contrary, it elevates it. It makes our existence, our fleeting, precious moment of conscious awareness within this grand cosmic drama, all the more miraculous, all the more precious, and utterly astounding. This is truly the greatest story ever told, and we, somehow, are living right in the middle of it,